From the University of Wisconsin-Milwaukee, The Science Bag, the television series where faculty members from university science departments share their special interests with you. And now, sunlight and ice crystals in the skies of Antarctica with Robert Greenler, Department of Physics.
I have gone to the ends of the earth to get material for tonight's program. The first time I went to one of the ends was 21 years ago when I went to the United States Research Station in Antarctica, located right at the South Pole. I went to study optical effects in the sky that come from minute ice crystals tumbling through the atmosphere. I returned this last year and spent 2 months at the South Pole. In between, I spent some time at Point Barrow, Alaska, in the Arctic. So I have lots of material. In fact, that's one of the problems I have tonight. I have too much material, too many things that I want to tell you. I have the feeling that if I told you I went to the South Pole to look at things in the sky and this is what I saw, you'd say, yes, but how did you get there? How did you sleep? And so I decided I'll take about half the time to talk about Antarctica and operating there, and then half the time to talk about things in the sky. I have another problem, and that is I carry a gene that makes me want to explain everything I mention. So I'm going to have to work against that tonight, or I'll keep you here longer than you want to stay. I have some very skeptical friends who said before I went, they said, look, you're going to go away and you're going to say you went to the South Pole, but how do we know that you just didn't go somewhere where there was snow and take some pictures and come back and tell us a story? I thought about that for a while, and I finally thought that I had the solution. I will show you one picture which I think will convince the most skeptical of you that I actually did what I said. It's the picture of the South Pole as you know it exists. Well, it's not an easy place to get to. Let me tell you about the route that I took. It took 6 airplane rides in 6 days to get there, and I was fortunate with the weather. Now, I started off, the first flight, perhaps not too exciting, was from Milwaukee to Chicago. Then Chicago to Los Angeles to Auckland on the North Island of New Zealand, and then down to Christchurch on the South Island, which is a staging area for all the United States research activity in Antarctica. And then the real trip began. In a cargo plane, an LC-130 Hercules, which took off in the summertime in New Zealand, on wheels, of course, and weather permitting, lands 8 hours later on Ross Island at the McMurdo base in Antarctica on skis on the sea ice. Now to show you where Antarctica is, I have to go to an Antarctic map here. As I've already illustrated, it's a little hard to know which side is up in Antarctica. And to make this map match that one, I should turn it upside down. But McMurdo Station is here. The last jump, then, is one where the plane takes off and flies to the pole, an 800-mile jump, and lands on the snow runway at the South Pole Station. McMurdo is the nearest approach to the pole by sea of any place on the continent. It's easy to talk about Antarctica as a place. And people ask me such questions, well, like, what's the weather like down there? Well, Antarctica is a continent. It's bigger than the United States and Europe put together. It's a continent that has many different geological formations, many different climates, many different habitats. And so asking what's the weather like in Antarctica is a little bit like saying what's the weather like in North America. Not a very sharp question. I lived and worked for 2 months on the polar plateau, the center part of Antarctica, which is covered by here by a 2-mile thick sheet of ice. It's a very different place from the coast. Around the coast, you have lots of life. And at McMurdo, for instance, I saw seals and penguins and whales and seabirds. But inland on this polar plateau, on this sheet of ice, it's a very different matter. And this is the part of Antarctica that I'm going to talk about tonight. The facilities were there for me to live and work. Think what the people were faced with who first went there to build that station. They could use the local raw materials, which were ice and air and nothing else. The nearest rock was 2 miles away, and that was straight down. So everything that's necessary to sustain life and to enable us to live and work there had to be brought in. I think that's an interesting effect. People, the first 5 people to walk on this part of the earth would be the Norwegian explorer Amundsen and his 4 companions, who arrived in December of 1911. The next 5 were the British explorer Scott and his 4 companions, who arrived a month later in January 1912, and in fact who died on their attempt to get back to the coast. So that's 10 people. The 11th person to walk in this area was the first person who got off of the United States airplane in 1956, which landed to start building the station for a global research project known as the International Geophysical Year in 1957. So this has not been a very highly traveled place. I figured that when I was there before, there probably had been, including all the people who flew in and got on the plane and flew out, there probably had been less than 2,000 people there. And even this last time when I was there, the total number was probably less than 10,000. Not a very highly traveled part of the world. So 21 years ago, when I went to Antarctica, I flew in by the Herc, which taxied to a stop at the South Pole and never turns off its engines. They would taxi up to the pole here. You can see the station in the background. And if the pilot or navigator had not been there before, what you would see is the pilot would get out and take the navigator's picture, standing next to the pole. Then they'd switch camera and they'd take each other's picture. And of course, if you happen to get interested in reflections, well, you can do different things. But then after they loaded and unloaded what they brought, they would jump back into the airplane and take off. And those of us who had been there a while would say, ha, and they didn't even see the pole. The actual pole was about 250 yards away, marked by this copper stake driven in the ground or in the ice. And people had put up signs telling how far it was to their hometown, to Walla Walla, Washington, or Minneapolis, or wherever. Well, let me tell you what it's like when I went this time. Landed in the same Hercules LC-130, which taxied up to the pole and stopped without turning off its engines. Not so different. That pole, of course, now that I'm talking about where the plane stops, is the ceremonial pole put next to the runway so that people can take each other's pictures when they get out of the airplane. The pole is surrounded by the flags of the nations that signed the original Antarctic Treaty. Now, however, the real pole is only about 100 yards away, and it's marked by a stake here, a USGS survey marker, which we put there January 1st of this year. Now, there's another one back here, which was put January 1st of the previous year, and the previous year, and the previous year, and the previous year. And I thought that this has really got to be one of the prime survey markers in the world. USGS people came and determined this spot as accurately as they could. And so, in fact, the person who made that is traditionally somebody who's at the South Pole. I thought that was such a neat marker that I commissioned him in his spare time to make one for me, and I brought it along so you could see it tonight. There is a survey marker that marks the end of the rotational axis of the Earth, and you might like to come down and look at that a little bit later. The person who made this, who is at the pole, I was there with him about a month before it came out that I was from the University of Wisconsin-Milwaukee, and it turned out that he had been a student here in the early 80s, and in fact, he figured out that he'd had me for a teacher in a physics course as a teacher. His comment was, "You didn't have a beard then," and I said, I didn't have a beard until about a month ago when I came to the pole, so it's a small world story. Let me show you something about the sun shining on the Earth. Right, you know that the Earth rotates about its axis once a day, and it moves in an orbit about the sun once every year. Let's see, let me just get this straight. Here's North America, and Antarctica, the South Pole, is the part covered by the washer on the bottom of this, the bottom of every globe. Now, if the axis of the Earth were perpendicular to the orbit plane, I think you could see that every point on the Earth would be in daylight for 12 hours and then darkness for 12 hours when it's in the shadow. But that's not the case. The axis of the Earth is actually tilted at an angle of 23.5 degrees. Now I think you can see that in this part of the year, which is the summer in the north, that someplace up here has a very long daytime and a short night. And I think by looking at where that line cuts down there, you can see that at this time of the year, the South Pole is in darkness 24 hours a day. Okay, but let's look at the situation 6 months later, when the Earth has moved in its orbit about the sun, its axis always pointing in the same direction in space. And now I think you can see from where that shadow line comes, you can see that the South Pole is in the sunlight 24 hours a day. And if you look up here in the direction of the horizon, you will see the sun 23.5 degrees above that horizon, and you think the Earth is standing still, you interpret what you see as the sun moving in a circle, constant elevation above the horizon around the sky, 24 hours a day. I arrived at the South Pole on December 16th. I crawled out of the dark cargo hold of this uncomfortable airplane onto the brilliant snowscape of the Antarctic Plateau, with the sun up 24 hours a day and this snow surface extending off to the distant, sharp, flat horizon in every direction. And I bet that even some of you who would never on this earth consider going to the South Pole could imagine the magic of being in that unique place on this earth. Is that right? Yeah, I would think that might be true. A question that people ask a lot is, how cold is it in Antarctica? Well, as I said, you have to be a little more specific in that. I'm going to be talking about the South Pole, not the coast, where it's much warmer, moderated by the presence of the ocean. I arrived a few days before midsummer, and the temperature was about 15 degrees below zero, typically. It reached the peak of the midsummer heat wave this year on January 9th, when the temperature got up to 4 degrees below 0 Fahrenheit. And then it started to get colder. I left on February 14th, where the temperature read minus 44 degrees. Now, people were getting a little bit nervous because they don't allow planes to land or take off when the temperature gets below minus 45. We had begged to stay till the last minute to try to catch the effects we were looking for, and February 14th was the last minute. 2 days later, the 16th, they evacuated the remaining people from the pole, except for the 28 who are wintering over and who are there now. In fact, they're there, dead or alive, until the next plane, which is the end of October. That's a little different commitment than I was making. I said that the sun was circling around the sky at the same elevation above the horizon. That's not quite right. After the 21st of December, every day the circle was a little bit lower. That is, it was spiraling down to the horizon, where it would reach, which it would reach shortly after March 21st, not to be seen again for 6 months. I looked at last year's records to see what the coldest temperatures were. In July, there were 9 days when the temperature was below minus 100 degrees. The coldest day of the last winter season came on September 15th, when the temperature got to 113 degrees below 0. So that's pretty cold. Let me show you some pictures about the pole station. The geodesic dome is sort of the symbol of the South Pole Station. And you see here some arches, which I will talk some more about. You see them here 21 years ago, but you won't see them now because the snow level has risen. If you walk in the front entrance, in between two of those arches, you see this. Here's a wide-angle picture. If you go to the right, you go into one of these arches where the generator, which produces electricity and heats the water and so forth, is located. To the left in that arch is the fuel arch, where the fuel oil is stored in big bladders. This is the life substance that makes things possible at this station. If you go straight on down this tunnel I showed you, you move into this geodesic dome. You see a tracked vehicle there, a Sprite, and some other buildings inside the dome where we eat and some people sleep and have some recreation and some laboratories. There's no problem in finding a place to keep food frozen. It's the biggest walkout freezer in the world. If you want to keep it from freezing, you have to have a refrigerator with some heat in it, of course. You look up at the dome. This is a fisheye picture of the dome. The dome is open. There are windows up there. It's not heated, but it keeps the wind and the blowing snow off the buildings and makes it much easier to operate. When I was there before, I walked out to the end of the runway one day to take this picture looking back at the station. And the picture is interesting to me because it really suggests how fragile the protection of that habitat is against the harsh climate of Antarctica. We spent a lot of our time centered around well, here are the pictures seen from this year. The familiar dome, but the snow level is about 25 feet higher than it was. The dome and structures are being slowly buried, and this year they started to build a new station, which will be completed in 2005. One of the results of this is that there are a lot of construction workers, and the station, which was built originally to house about 40 people, now we got up to 196. things were rather crowded. There are some new dormitories that have been built, but it's crowded. On this day, you see there were some small planes in. There's some twin otters, which were used to get people around Antarctica to a field site where there was no permanent camp, where people would live in tents while they were doing some research project. Off here, and this is a kilometer away, about 6/10 of a mile, is something called the dark sector, where they have three large telescopes, an infrared telescope, a microwave telescope, and a radio telescope, and also an experiment which puts detectors down into the ice that detects neutrinos coming from exploding stars, neutrinos which have passed all the way through the Earth before they get here. Now, I scanned across here partly to show you that there's nothing to see. As I come around here in this direction, I approach something which they call the clean air sector, upwind from the station, where they try to keep away all activity, because what blows in from that direction is probably the cleanest air in the world. If you look off in that direction, here's a building called the Clean Air Building, where they measure a number of components of the air. If someone walks out in the clean air sector, they can see the rise in CO2 from a person breathing out there. Here are the halo shacks, which I'll talk more about later, around which much of our activity was centered. There's two of them. The nearest, off in that direction, the nearest inhabited place is South Africa, about 5,000 miles away. And off at the edge of the clean air sector is a device which I took down and put together, which was to take time-lapse pictures of the sky, and in fact, you see it here tonight. I'll talk a bit about that later. Before I tell you what I was looking for, let me tell you a little bit more about operating at the South Pole. I mentioned my skeptical friends. Several of them, or many of them, are very interested in winter activities, and they spend time outside, and they said, what are you going to wear? How are you going to keep warm? And I said, I don't know. I'd be interested to find that out. We get outfitted with extreme cold weather gear in Christchurch, and I'll be interested to know what it is. So I thought when I got to Antarctica, it would be interesting to take a photographic series of the clothing. And so I went out one night. Of course, night is an arbitrary term. I went out one time when most people were sleeping into a lab that was vacant, and I started to take pictures of the clothing. Well, of course, the place you start is the first layer. And I was a little bit concerned about this. While I had this self-timer on my camera, standing there in my underwear, I thought, what am I going to do when someone comes in and says, oh, pardon me? I said, no, it's all right. Come in, I'm just taking pictures of myself in my underwear. And, the more you explain, the worse it gets. Well, actually, no one did come in, and I took the series, and I showed it at a science bag in January 1978. And I've had the experience several times since then of meeting someone at a social event, and I see this dawn of recognition saying, oh, I remember seeing you standing in your underwear in front of a large group of people. Well, I thought I might as well show you those pictures tonight. So here's where you start. Actually, there's another layer under that, but I didn't get, no use to get too explicit. Over that goes a wool shirt and at this time, some pile pants. The boots, there are a couple different boot systems, but this is one, and there's a mesh insole, and then a heavy felt insole, and then a fleece bootie that all gets inside and laced up inside the boot. A warm jacket. A variety of headgear, in fact, which can be worn in a variety of manners. And I had a little additional not a standard issue, something my mother-in-law knit for me before I left. Just in case I needed a little extra protection. The parka can be worn if it's windy. You can fold it out to keep the wind off the skin. And so here is the way in 1977 the well-dressed Antarctic scientist would be attired. I show you a picture from this year of the three of us working on this project. And you see the clothing doesn't look too much different, but we've changed the color of the beard. Who you see here, my two colleagues on this HALO project. On the left is Gunther Kernen, meteorologist from Holland, and on the right, Walt Tape, who is a mathematician from Fairbanks, Alaska. So much of our activity was centered around the HALO shack, so let me show you some pictures of that. There are two buildings here. The one on the right had been used as a HALO shack before. The one on the left had been used by Nikolai last year, and he had labeled it Nikolai's Institute. Well, we brought it up to date, calling it the Tape Kernen Greenler HALO shack for 1997-98. So come on inside and see what it looks like. The inside looks a little bit bigger with this wide-angle camera. It's about 10 by 16, place to store equipment and cameras, place to work on things which seemed constantly to be going bad. As I said, the station is getting quite crowded. It was a pleasure to have this. In fact, some of the halo effects that we talked about, that we were interested in, came and went so quickly that we slept out here frequently in these shacks so that we could be ready at moment's notice. Looks like I didn't make my bed very well that morning. But it was a pleasure to have a place where you could sit down and spread out some things and work, which was a scarce thing in the camp. Well, I decided that things were not sufficiently different that I needed to go through another sequence this year. The boots were a little different, but the system was similar. You had to get everything on in the right order. You know, if you leave out one of the insoles or you put the boots on before the pants, then you have to go back and do it differently. So here's a couple pair of underwear, jeans below, flannel shirt above, these pants, and then the jacket. When I was there before, they did not use down jackets, and that was kind of interesting. The reason, as I understand it, was that there are some people who are working out for extended periods, and if you happen to rip the jacket, you just lose the feathers out of that little place, and that just means you just freeze the flesh in that little place. And so they use something which was more rugged. Well, they do use down jackets now, but they have a very tough shell on them. If you don't get things on in the right order, you have to go back and do it again. So this is a neck gaiter, which shields the neck, and it's, depending on what the wind chill is, worn in a variety of ways. When the wind chill gets down to in the minus 50s or minus 60s, you need to cover things up. If you have just your nose exposed, what it means is after a few minutes you'll freeze just your nose. So the goggles made a good seal for this. You could, if the wind were blowing, for me this was warm enough for the temperatures we had if I was outside for an hour or so. If I were going to be out all day, I would have probably had another layer on. So that's well-dressed. So here's the instrument which I called my R2-D2 for obvious reasons, and I'll tell you a little bit more about that later. It scanned around the sky, following the sun, taking time-lapse pictures of the halo effects that we were interested in. And so the thing that we had come to Antarctica to study were ice crystal effects, the most common of which is this big halo around the sun. You see that here frequently. Now, we were interested not only in the effects, but we were interested in the ice crystals that cause them as a way of understanding what's going on. So we also collected ice crystals. And here's Walt, my colleague Walt in the middle, and two other visitors. We had kind of an open house. Will, the doctor on the right, the camp doctor who is in fact wintering over now there, and Erica, who is one of the summer workers. Walt is pouring hexane, which is whatever the outside temperature is. It's been sitting outside minus 30 or something, into a little dish and waiting for ice crystals to fall into it. If you catch the ice crystals on a glass microscope slide, you start to look at them. They don't melt, but you see them evaporate. So this makes them last a little bit longer. Well, on this particular day, there were a number of ice crystals, of optical effects in the sky from ice crystals. And so people were looking at that, and after a certain length of time, you say, well, all the time you're having these little ice crystals fall into the dish, and so you say, well, that's enough. We'll take them into the shack and look at them under the microscope. Now, we'd cool the shack down to about 30 degrees when we did this. Bye, Will. But the microscope was put in a little wooden well here with there's a window open to the outside, so you could fill this with cold air, and it might be around 0, colder than the rest of the room. There's always an excitement to see what you have. Usually a collection of, you see little hexagonal plates here and all kinds of ice crystals. Now, Erica is very much impressed with what she sees in here. In fact, Erica looks at this and says, wow. Look at the bubbles in this. We have no idea why this grows with these little openings. Beautiful, beautiful example. See some more crystals here with intricate internal structure. Very beautiful. These would probably produce lousy halos, but certainly there's some beauty in these halos, in the crystals themselves. I think there's an excitement about looking for this, which I think is a little bit the excitement of fishing. You put out this plate and you don't have any idea what you're going to get, and you look in and it's exciting to see what kind of a variety you can find among those crystals. So we're interested in the crystals that produce the halos, and it's to understand these halos that brought us to this end of the Earth.
If you'd like to continue this program at another time, this might be a good time to stop the tape and take a break.
I'm going to talk quite a bit about two shapes of ice crystals. I'll call this a plate crystal, and I'll call this a pencil crystal. It's shaped like a wooden pencil before you sharpen it, right? They're both hexagonal in cross-section. If you send light in this side of this crystal and out this side, let me just show you. It's the same as if you sent it through a triangular prism, right? As the fact that you cut off the corners doesn't change the path of the ray which goes in this face and comes out this face. That's a little more familiar optical element, that triangular prism. So let me show you some light going through a triangular prism, in this case of water, which will have about the same optical properties as ice. So projector, I have a spot on the wall there, a beam coming up here, so let me move this into the beam. And off to the side there, you see that the light has gotten deviated, originally headed toward this slit on the wall, and going through the prism, it gets deviated over to the side. Now, the angle of that deviation depends upon how I rotate this prism. But the point I want to make is that I can rotate this prism through a pretty wide angle, and that light doesn't move very much. In fact, it concentrates at an angle about 22 degrees away from the direction that the light was originally going. Now, if you have a whole bunch of crystals in the sky that deviate light by 22 degrees, the light that comes to your eye you see from crystals that are 22 degrees away from the sun. That's not just one direction, but it's a whole circle around the sun. It's the halo of which you've seen several pictures, called, not surprisingly, the 22-degree halo. So what I've told you is that the light that comes through here, it's coming through a 60-degree prism angle. But this crystal also has some other angles in it. The angle between this face and this face is 90 degrees. And you can have light go through a 90-degree ice prism coming in here and out there, and it gets deviated by about 46 degrees. And so there should be a bigger halo, too, with the angle of 46 degrees from the sun. And you can see both of these. I have a photograph here of a meteorologist named Alistair Fraser, a wide-angle picture showing both that 22-degree halo and the 46-degree halo. Now, the 22-degree halo is much more common than the 46-degree halo, and in fact, around here, in most of the United States, you can see the 22-degree halo if you look rather frequently. Now, to get the complete halo, you have to have all random orientations of these crystals. Now, I'm going to make a claim here that if you drop crystals of this shape, made of ice, a fraction of a millimeter in diameter, if you drop them in still air, they don't tumble randomly, but they tend to orient. All right, I'm going to ask you to take this multiple choice quiz and tell me how they orient. Now, you know, you've all taken quizzes like this. You know how to do it. If you don't know the answer, you guess. Okay, I'll give you the two choices. Two logical choices would be that they would tend to fall on edge like that, or that they would tend to fall flat. So make up your mind, and I'll have you hold up your hands. How many people would predict that these crystals should fall on edge? Hold up your hands. How many people would predict that they should fall flat? Ooh, there seems to be a bit of a majority there. It's hard to get at the truth reliably that way, though, isn't it? Okay, I'm going to do the demonstration for you. I have a whole snowstorm of crystals up there. To make them orient, the bigger they get, the lighter they have to be. So some of them are going to be very fragile, and when you come up, don't walk on them later. I'll drop them, and you look to see if you can detect some orientation from these crystals. You ready? Okay, in case you didn't see that, let me give you an instant replay. And one more time. Okay, look at some of the ones off to the right at the end. And I think you begin to see the motion, right? Okay, the motion that you see is this. And of course, it's always easier to get it right once you know the answer. You begin to think about how leaves fall off a tree, and that's right. So what's the consequence of having a sky full of ice crystals with the, and in fact, sometimes when you get crystals just the right size, that orientation is so good that they really settle very flat. If you have randomly oriented crystals, you get the complete halo. But if you have the crystals oriented with their big surfaces flat, you see only the parts of the halo at the side. Now, here's a picture that some of you have seen used for publicity for this talk, and it really is a fraud, because the talk advertised Antarctica, and this picture couldn't have been taken farther away on this planet. It was taken in the Arctic at Point Barrow. And I had taken it and thinking I would find some use for a picture of me pointing to the sundogs. And we won't spend any of my time discussing the personality of somebody who takes a self-portrait looking like that. But I have some Antarctic photographs too here. Now here's a case where almost all of the ice crystals in the sky were oriented as we've showed you with those bases parallel. And you see the bright spots on either side of the sun. They have many names, but the one I'll use is sundogs. Here you see a sundog, and you also see a trace of the halo. So there's some crystals that are oriented and some other crystals that aren't. They might be in a different layer. They might be a different size. I don't really know that. And just to prove that sometimes you do get a lot of little hexagonal plates, as I showed you here, I show you this picture, which shows quite a few of them. I thought it would be nice to show you, to produce a sundog right here as a demonstration. Well, for that I need the sun, no problem. I've got the sun. Now, I'll tell you what I had in mind. When I first started to think about this, I said, okay, here's a place out here. And if I could get 1,000 little crystals shaped like this, tiny crystals, transparent, and suspend them in space with these faces horizontal, but let them have any orientation like this, random orientations like this. If I had 1,000 of those in this little volume, some of them would deviate light off to the left and some to the right. And from what I've told you, there should be a concentration there at that sundog position. And you should see a sundog on either side of the sun. Well, that was a good idea. But the problem was I never figured out how to get those 1,000 little ice crystals in there. The best I could manage to do is to get one. So I have one here. Now you can see that as I turn this, as you saw before, as I turn this, you see the light deviated from one side or the other, and it moves around a little bit as I rotate this. But if instead of having 1,000 little crystals, each with a different orientation, I have only one, but I change its orientation so fast that your eye can't follow it, but only kind of see the average, I should produce a sundog on either side of the sun. How about that? Do I see some of you pointing up to the top and say, yes, there's another arc up there, a very bright arc. It's the circumzenithal arc, and I will show you some pictures of that later. Okay. Now, let me tell you something. There's some things that aren't obvious about that demonstration at all. There are two ways that I can produce sundogs. Nature's way is to, with the sun back there, fill the sky with millions of ice crystals, oriented like this. And you look over at a particular place and you see a crystal which is oriented such that it sends light to your eye from 22.5 degrees. And up there is another one that sends it from 22.6 degrees in that direction. And so it takes millions of these little crystals to give you the whole circle. There's a concentration of crystals about 22 degrees away from the sun that send light to your eye. That's the way you see sundogs in nature. What I've just done is to use one crystal. I've shined light through it onto a screen, and I use only one crystal, but I give that crystal all of the orientations of the millions of crystals you have in the sky. And in fact, I have to do that so fast that your eye can't follow the motion. So, what I've done with one crystal here is to reproduce what you see in the sky done with millions of crystals. Okay, let's do something. Let me show you another effect with the same idea. Here's a photograph of a halo. And you see the sundogs, but you see a spot of light at the top of the halo also. In fact, that spot of light takes the form of an arc which touches the halo. It's called the upper tangent arc. Its tangent means touching smoothly. And we know that that comes from these pencil-shaped crystals, which orient as they fall with their axis horizontal. Okay, so as these crystals fall, you might expect that they will have a horizontal axis, but you would think that they would have any orientation like this, and of course they could point anywhere in that horizontal plane. So how would we, with one crystal, simulate that? Well, we'd have to spin it about this axis, and then we'd also have to spin it about a horizontal axis, about a vertical axis. Now, let me say this again. I'm not spinning this crystal because the crystals in the sky are spinning. I'm doing it because I have to give this crystal all the orientations of those millions of crystals in the sky, and I have to do it so fast that your eye can't follow it. Well, I have a little crystal here, and this one's made of plastic, and I have it mounted with a little motor here run by batteries, so I can spin that pretty fast. Okay, and then I need to spin it to give it all the orientations of one of these pencil crystals. I have to spin it about a vertical axis, so I brought my drill from home. So now I have it spinning about this axis as I rotate it about this. And I see that upper tangent arc, which we see at the top of the halo. How about that? Okay, let's just check that out to see whether that in fact does have the shape of that upper arc. And I think the answer is yeah, it reproduces it pretty well. Actually, the shape of that arc depends upon the elevation of the sun. And if I tilt that, I can represent the way that the shape of that arc changes with the sun. So it really gives us a pretty good indication. I'm going to show you now some of the kind of video pictures that I took with this device here. Originally, I didn't have this cover over it. I was worried about keeping it warm enough. What we have inside here is a video camera and a motor that drives this at the speed so that it follows the sun. I have a shield out here to keep the sun off of the lens, some heaters, and I was, of course, worried about keeping this warm enough for everything to operate. And one of the first days I put it out, it was 15 degrees below zero out, and it was 60 inside the bag. I had a thermometer in there, and I said, the heater system is not working. I turned the heaters off, and it stayed 60 degrees. And I was amazed to realize that the Antarctic sunshine was acting as a solar heater, keeping this bag much hotter than I wanted it. Well, that's when there was no wind. When the wind blew, then it leaked and everything got cold. So I made an evening dress for R2-D2 out of a space blanket, which reflected some of the sunlight in the daytime, and it kept some of the wind off when the wind was blowing, and it made it easier to regulate the temperature. This tracked the sun, and I took pictures like this. The shield is covering the sun, and it's scanning around to the left, which makes it look like the horizon is moving to the right. Here's the dome of the station. At this particular time, there had been a lot of clouds going over, water droplet clouds. Even though the temperature is well below zero, it cleared, and all of a sudden, we started to see some interesting things. Now, you have a clear blue sky. You think there's nothing there, no ice crystals. But I want you to look carefully around here, and you'll start seeing a few white sparkles, because all of a sudden, some crystals started to fall all around us. You see the flash there? You see a few, and in fact, you'll begin to see a concentration of things up here, forming that upper tangent arc. You see the streaks, the wind was blowing quite a bit, flopping the shield around. You see the 22-degree halos, an arc that goes all the way around parallel to the horizon, this upper arc, and once in a while, we'd see sort of a rare arc which filled in this which tended to arc over the top of this upper tangent arc. Now, I stopped the tape here. You see, the upper tangent arc normally looks like this, and here is an arc which is called a periarc, which goes over the top of that. Now, it's called a periarc, named after the person who reported it. He was a British explorer looking for the Northwest Passage in the early 1800s. Here you see at the top his original drawing of this, and there are a lot of things, but the arc that bears his name is this little arc that comes across here. And just to see that we understood it, we did some computer simulation to see if we could reproduce things, and I think we did pretty well, which meant that we really had figured out what the periarc was all about. We took pictures of that arc. I think you see at the top of the halo there, you can see that arc. And you can see it here. What we understood was that, and this is a surprising result, that occasionally when these crystals are just the right size, that in addition to orienting so that this axis is horizontal, they orient so that this surface is horizontal. That is, they'll fall with slight tips about that, so they're doubly oriented. And if you get a crystal like that, you get this periarc. Here's a picture of, this is a picture of Walt tapes, and I think you can see that periarc across there. That's, if you get those crystals oriented, then you should get a whole bunch of other things too, from light that gets reflected off the surface and goes through the ends and takes a bunch of different paths. And one time before most of these things had ever been seen, a colleague and I simulated these with a computer program, and we got this. Now that's really very complicated. Here's the sun, the halo would fit in here. Here's the periarc, and a bunch of other things. But for instance, these little hooks out here, nobody had ever seen anything like that. Well, I'll show you a simulation done by Walt Tape. showing a fisheye picture of the sky for a slightly different sun elevation. And you see all of these effects that I've been talking about. For instance, look at those little arcs specifically. Lots of stuff. Well, what would we have to do with our spinning crystal to simulate those? Well, think about it. This axis has to be horizontal. Okay, that makes it easy. This face stays horizontal. That makes it easy too, right? We don't have to spin it. In fact, all we have to do is take this crystal. It should have all of these orientations. So all we have to do is spin it about one axis. Well, let's give it a try and see if we can see any of those things. All right, I have a water-filled crystal here. So that it has the optical properties similar to that of ice. So now I'll spin this crystal. And see if we can see some of those things that our computer simulations suggested might be there. It's dim. You dim that down a little bit. Well, you see the periarc there, don't you? You see these lines here which are reflected off surfaces. You see those little hooks up there? Let's see, let me turn this off for a moment. See those little hooks? And in fact, some down here, all of which are simulated. We hope to see those things. We hope to see more of these things. When we did that first simulation, nobody had ever seen these things. But on a previous trip, not this one, Walt Tape had some pictures which showed this. Now, could I have a slide on the left screen there? An all-sky picture, which looks like the simulation. That's no surprise because the simulation was made to look like the picture. A fisheye lens looking up, and you see a faint representative of those little hooks out there. Never had been seen before. There's one more picture of this. These are very rare pictures. And I think you can see them there. Of course, there are other things here also. They're not all of these doubly oriented crystals. Well, I think that's interesting. We see that we can reproduce with this simple model spinning crystal what we reproduced by the computer simulation, and it appears to have some reality for some of the things. Some of the things we haven't seen, and we did not this year, and hope that we would. A lot of things come from these two crystals, oriented. Let me show you some pictures that show a few more effects. You know, and I shouldn't get in such a hurry in showing you these things to neglect to point out my reaction to this is that that's a beautiful picture. Can you imagine stepping outside and looking in the sky and seeing this? You can see some of those things here. But this is truly a magnificent picture. And you see up at the top of this halo, this circumzenithal arc, which I showed you on the first spinning crystal. Sometimes that's brilliant, and it's brilliantly colored. When people ask me here, and I get this question every now and then, people say, what was that rainbow that I saw at the top of the halo, or above the sun? And I can say, that's that circumzenithal arc. It comes from rays that come in the base of the prism and out the side. And it can be brighter than the purer colors than the rainbow sometimes. Brilliant, brilliant. So there are many more effects that come from these two ice crystals that I've showed you than I am going to talk about tonight. Let me just point out a couple here, which I won't talk about. You see an arc here at the bottom of the halo also. Instead of the 46-degree halo here, do you see that this is an arc that bends out? Oh yes, there's lots of things. We can explain many things with these two kinds of crystals, but there's one class of things which we have been unable to explain with that, and I will show you an example. Here's a picture which Walt took in Alaska, which has some halos of very strange sizes that don't seem to be explained by coming through this crystal. These halos are not very well documented, nor are the crystals that produce them. There's the thought that sometimes, or there's the knowledge that sometimes a hexagonal crystal like this gets pyramids growing on the end. The pyramids, the crystals are not very well documented, and we hope to get some pictures of these halos and catch the pyramid crystals that were producing them. And in fact, one night, Walt stayed up all night taking pictures, and he got some of the best pictures in the world of these pyramid crystals under the microscope. Now you see very clearly, you see those little pyramid faces on the end. In fact, that's so good that you can measure the angles, and we can learn something from that. Well, of course, we wanted the crystals and the halos. There were supercooled water droplet clouds giving a white light to the sky, which masked all the fainter effects which should have come from these crystals. We got half the story. We got the crystals, but we didn't get the halos. Let me end by telling you about one more effect, which we hope to see. And to do that, I need to tell you a story which starts 15 years ago. I spent several months in a laboratory in what was then West Berlin, working on a research project which had nothing to do with crystals. But once a week, on Wednesday, I got together with a colleague from the Free University in West Berlin. We got together for lunch. This was someone who was interested in all of these ice crystal things. And we worked on investigating some things that happened in the sky on the opposite side of the sky from the sun. Same elevation. It's called the Antarctic point. And we figured out that there were a lot of things, some of which had been seen and some of which hadn't. And we published a paper on this in the British journal Nature. And the title of the paper was Antarctic Arcs from Airborne Ice Crystals. And in that paper, we did simulations in which we had, for different elevations of the sun, 0, 5, 10, 15 degrees. And a series across here were different arcs that resulted from rays that took different paths through the crystals. Some of these were known and some of them weren't known. Now let me just concentrate on a couple of these arcs, which were not really very well known or predicted for when the sun was 20 degrees above the horizon. These arcs are not very sharp, and we named them the diffuse arcs. We had only a couple of very poor pictures of these, but these were our predictions. And we ended this paper saying, now we really need to wait for pictures of these arcs to test our predictions. Well, we called them the diffuse arcs. There are some people who have called them Greenler arcs. And so I had hoped to get some good pictures of these Greenler arcs on this Antarctic trip. A few days, about a week after I arrived, when I still didn't have my cameras up and operating, I got a breathless call over PA system from Walt saying, get out to the Halo Shack. Walt, who had been alerted by one of the construction crew that there was something interesting going on in the sky. As I was in the dome sending an email message, and as I rushed out, I saw the brightest display of these diffuse arcs that I had ever seen. and stuff all over the sky. And I rushed out to the Halo Shack, and by the time I got there, everything had disappeared. The whole display lasted less than 10 minutes. Well, I'd only been there a week, so surely I was going to see many more of these. This was a good omen, right? Wrong. January turned out to be the cloudiest January on record at the pole, and the clouds were not ice crystal clouds, but they were supercooled water droplet clouds. Why? I don't know. I saw a couple of times these arcs that some people have put my name to, and I have a poor picture of a display that was nowhere near as good as the one that I didn't get. I'll show you a poor picture and see if you can see anything in there. Let me dim this down a little bit. That looks anything like those diffuse arcs. Can you see an X across there? Well, it was not as good as what we didn't get. So let me ask you the question. If you were I, wouldn't you like to go back to Antarctica and get the definitive picture of those arcs that bore your name? Yeah, I think I might have to do that. I wonder if you would indulge me for a few more minutes to take a look back at the first 25 years of the Science Bag. Of course, I've been involved in that from the beginning. I made the decision that 25 years is a good time to turn it over to someone else. And so Professor Norman Laska of the Department of Geosciences is going to become Science Bag Director next year. This is the last program of this 25th year. And in a sense, it completes another cycle for me. I went back to dig out of my files the announcement for the first program of the series, which was in December of 1973. And this is what I found. Well, it was a very different program, but in fact, tonight, you see, I did touch on halos and sundogs, and I hope you think I touched on some other neat effects. But in between that program and this program, I've also talked about how musical instruments work, about mirages and light scattering in the sky, and spinning tops, and color mixing, and how the eye works, and global air circulation, and soap bubbles, and many other things. And in fact, 61 of us from this institution have given 600 programs to which 120,000 of you have come. In fact, when I look around tonight, I see quite a few familiar faces. I think several of you have gotten counted several times in that 120,000. So I have enjoyed being involved in this, and I appreciate you being involved in this for the last 25 years. I think the way to look at it is we had a pretty good run, and I view it as we're ready to start the next 25 years, and I wonder what you think. Will you come? I hope so.